first time I flipped it, I saw a heads. Second time I saw a tails. Third time a tails. Tails again is showing the picture of the sailboat from Rhode Island. Heads is the picture of George Washington. The fourth time I got a heads. The fifth time I got a tail. The sixth time I got a heads. Then I got 3 tails in a row, and then I got a head. So this is what my data is from this 4 heads and 6 tails. Now, what's the probability of observing what I actually saw? What's the probability of flipping a coin 10 times and actually seeing these results? What is the probability of getting a head, and then a tail, and then a tail, and then a head, and then a tail, a head, a tail, a tail, a tail, and a head? Well, each time I flip this coin, it's an independent experiment. The side of the coin that showed on one flip of this coin won't influence the side that will show the next time I flip it, because every time I'm picking the coin up and throwing it in the air. So that the probability of getting this sequence of heads, tails, tail, heads, tails, heads, tails, 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 and heads is going to be the product of 10 probabilities. Probability of first flipping a head, and that's what the number of the letter P stands for. P is the probability of getting a head, multiplied by the probability of getting a tails. Well, since you either get a heads or a tails when you flip this coin, the probability of getting a tail will be 1 minus P. And the probability of getting a tail on the next flip will be another 1 minus P. Then the probability of getting a heads on the 4th flip will be a P. Getting a tail on the 5th flip will be a 1 minus P. The head on the 6th flip will be a P. 3 tails in a row will be 1 minus P, 1 minus P, and 1 minus P. And then lastly, on the last flip, getting a heads, the probability of seeing that will be a P. So the probability of observing that which we actually saw was P times 1 minus P times 1 minus P times P times 1 minus P times P times 1 minus P, 1 minus P, 1 minus P, and P. Well, that's nothing more than getting P 4 times. That's P raised to the 4th power. Times 1 minus P 6 times. That's 1 minus P raised to the 6th power. That's what we call the likelihood function. It's the probability of observing what actually happened in your study. In this case, the probability of observing 4 flips that came up with heads and 6 flips that came up with tails. Now what we want to ask ourselves is, what value for P maximize this expression? What value of P gives me the biggest probability of observing that which I actually had? Flipping a coin and getting 4 heads and getting 6 tails. In other words, what value for P, if I plug it into this expression, take that number and raise it to the 4th power, subtract that number from 1 and raise that quantity to the 6th power, will give me this probability, which is bigger than any other value of P will give. So that's what I'm trying to ask. What value of P maximizes the likelihood, maximizes the chance of getting what we actually saw in this study? And that value of P is what we call as the maximum likelihood estimate, because its value maximizes the likelihood. Now, if you think about it, if I ask you to make a guess and say, what do you think is the maximum likelihood estimate? What value for P would maximize this expression? You might have a guess in your mind. Patrick says 0. Other people might say, hey, it's a fair coin, Fran. It looks like a coin I have, so it's probably a 50-50 chance of getting a hit. P is 0.5. Some of you might say, well, you flipped it 10 times and you got 4 heads, so maybe 4 divided by 10 will be the maximum likelihood estimate. So the question is, how do we get the value for P? Well, one way of doing it is by hit or miss. Let's draw a little table. We'll take a value for P. The smallest P can be is 0. The biggest P can be is 1. Let's start by plugging in 0 for the likelihood. Put 0 in for P. Put 1 minus 0, or 1 in for 1 minus P. And what you'll have is the number 0 multiplied by itself 4 times, multiplied by the number 1 multiplied by itself 6 times. We know that any number multiplied by 0 will give us an answer of 0. So the value for the likelihood when P is equal to 0 will be equal to 0. Likewise, at the other extreme, if P is equal to 1, we'd be taking the number 1 multiplying by itself 4 times. Then we take the number 1 minus 1, which is 0, multiplied by itself 6 times. And again, all those zeros will give us a product of 0. So now what happens if we take a number between 0 and 1? And what I have here are four possible test cases. What if you took the number 0.1 for p? What would you get for the likelihood? You're taking 0.1 for p, multiplying it by itself 4 times. 1 minus p becomes 0.9. You'd be multiplying it by itself 6 times. If you do that, you get the expression 0.0001. That's the value for the likelihood when p is 0.1. If you put 0.4 in for p, to that same formula, you'd have 0.4 raised to the 4th power, 0.6 raised to the 6th power. You actually get a bigger number, 0.0012. So 0.4 is than the number 1, because 0.4 so far gives us a bigger value for the likelihood. A better explanation for getting 4 heads and 6 tails when you flip a coin 10 times. Get those results. What happens if you take a number bigger than 0.4? Well, if you took 0.5 for p, you'd have 0.5 raised to itself 4 times. And 1 minus 0.5 would again be a 0.5 multiplied by itself 6 times. You'll get the number 0.001, which is a little bit less than the likelihood when we use 0.4. If we use 0.9, we have 0.9 multiplied by itself 4 times. 1 minus 0.9 is 0.1 multiplied by itself 6 times. We get a much smaller number. So at least in these 6 candidate values, 0.4 gives us the bigger or the largest of these likelihood values. So of the 6 trial cases, 0.4 looks like it's the best. But how do we know there's not another value that we didn't check that would have given us a likelihood bigger than 0.0012? Because hit or miss is only as good as the values we try. And how do you know if we tried something else, we would have got a bigger value for the likelihood, and it would become the maximum likelihood estimate? Well, this is not the way we figure out maximum likelihood estimates. We actually use some calculus. And basically, it's built around this picture. What I've drawn here is a little bit of a curve. On the y-axis, I have the value for the likelihood. On the x-axis, I have the value for p, which can go from as low as 0 to as high as 1. And basically, what the likelihood curve would look like is this very upside-down U-shaped curve. We know that when p is equal to 0, the likelihood is equal to 0. We know when p was equal to 1, the likelihood was equal to 1. We saw that in the previous slide. P is 0, or when p is 1, notice the likelihood is the smallest it can be, 0. It got bigger as you moved away from 0 and as you moved away from 1. And what that means is this is what the likelihood curve would look like. It's concave looking downward. It's a nice inverted U-shaped curve. And what we want is the value for p which corresponds to the top of that curve. Well, I don't know if you guys took calculus sometime in your life. If you went to college and took a calculus course, if you're an MD, you probably would have had to take a calculus course. Now, my son and my daughter had calculus when they were in high school here. Well, calculus involves taking, among other things, taking derivatives. And what a derivative is nothing more than a tangent, a line that touches this curve in such a way that it shows how quickly this curve is going uphill or how quickly this curve is going downhill. Or in the case at the very top of the curve, how the curve is changing from going uphill to going downhill. It turns out that the derivative of this likelihood function at the top of the curve will correspond to a flat line. If we drew a tangent to that top of this line, it would be a line that would be a flat line with no slope. And that means the value for p that maximizes the likelihood would be the value for p for whom this corresponds to a first derivative, whose value is equal to 0, because that means we're looking at the top of a curve. So if you haven't had any calculus before, just sit back and look at this next slide for a second. If you've had some calculus, this is an exercise in going down memory lane. What we want to do is find the value for p for whom the first derivative of this likelihood function is equal to 0. Meaning if we drew a tangent line and it had a slope of 0, that means that tangent line would have had to be at the